Yeah, thank you for joining this seminar. Yeah, and today our speaker is Dr. Jaegon It's my pleasure to introduce him. And he got a PhD from the postdoc Department of Physics in 2008, and he has several research experiences after graduate, Busan National University, KIAS, and Biolchibrook University. And then he come back to Korea and he joined in KIAS and Seoul National University. Now he is in postdoc. So today, he is interested in thermodynamics and phase oscillatory superconducting array and mesoscopic systems. And today, I think this topic is related to the mesoscopic and thermodynamics. The topic is coherent effect in a multi-level quantum dot heat engines. Okay, let's welcome speakers.
Yes, thank you. Can you hear me?
Yeah.
Okay, so good afternoon, everyone. First of all, thank you for this opportunity to present my work. Today, I talk about, as introduced by Dr. Park, Kim. so today I talk about the quantum thermodynamics, focusing on the coherence effect through a quantum dot heat engine. So you can find that the almost textbook on thermodynamics treat the heat engines as an important subject. Indeed, it has been known that 2,000 years ago, an ancient Greek already designed a kind of heat engine extracting some energy from the heat flow from the reservoir to cold reservoir. I want to say that the heat engine is the heart of the thermodynamics. So not only in the practical aspect, also in the aspect of physics. When we talk about the engine, for example, in automobile, we mentioned the efficiency of the engine, defined as a ratio of the work and input heat energy. Everyone wants efficient engine whose efficiency is close to the 1, right? But the thermodynamics, especially the thermodynamics second law, says that the engine efficiency has the upper bound called the so-called the Carnot efficiency. It has been known that this Carnot efficiency given by this form is 1 minus Tc divided by Th. Tc is the temperature of the cold reservoir, and this is a hot reservoir temperature. It's achieved in the reversible process, right? So the Carnot engine is called the reversible engines sometimes. So recently, my group reported the irreversible engines, which can show the Carnot efficiency. This is the counterintuitive. This is contracted to the conventional knowledge about the thermodynamics. Anyway, so there's an interesting question more than this irreversible Carnot engine. Can you make the more efficient engine than the Carnot engine? This efficiency bound is a consequence of the thermodynamics second law with the Clausius entropy, given by this term. So this question is directly related to the seeking of the non-conventional entropy production other than the Clausius entropy. The thermodynamics started from the classical systems. After quantum mechanics developed, the thermodynamics of the quantum system has been studied with much attention. So-called quantum thermodynamics is the active research field, and heat engines composed of the quantum substances are one of the major topics in the quantum thermodynamics. A relevant question is that the quantum effect, specifically coherence, can be a source resulting in more powerful machine. The optical systems is a popular model for investigating the thermodynamics of quantum thermodynamics. Quantum heat engine, which consists of the photonic heat basis, system with a few levels, and work storage. This one I just Yeah, just one. This kind of engine is well summarized in this paper, and recently it's realized experimentally in this paper, reported. In short, if the random wave approximation or scalar approximation works in the system, engine system, thermodynamic property is just obeys the conventional thermodynamic second law. Nothing different from the classical thermodynamics. Yeah, of course, this coherence can enhance the power, but in terms of the entropies, is just equivalent to the classical thermodynamics. On the other hand, this group showed that the quantum coherence caused by the bath here, so can survive in the steady state if there are degenerated levels in the systems. So here, the random wave approximation or scalar approximation is killing the coherence associated with bases. But if there are degenerated levels, these approximations cannot kill the coherence caused by the base. So it is reported that the coherence between the degenerated levels survive in the
question.
state. Okay.
Can I ask a question, please?
Mm-hmm.
So this random wave approximation is an approximation which we do in order to somehow easily and efficiently describe a time-dependent function which, say, comes from is a force which is coming from a bath, originating from, for instance, a bath of many degrees of freedom. But still, the bath could be, in some sense, evolving still perfectly coherent. So my first question is, since this is, I think, very interesting and important, the issue of coherence, decoherence, bath, and quantum, I mean, I could imagine that I have a bath which is really, in some sense, which loses, so to say, correlations in it, right? So which, where I can compute all kinds of correlation functions, and then we'll see that these will tend to zero after some characteristic timescales, and therefore I would assume that my bath is a truly incoherent source of excitations. On the other side, I can say, well, I just make a random wave approximation to make life easy for me when I want to calculate something, but the bath actually is still perfectly coherent even on these times on which I apply these random wave approximations. And on the other side, sure, if you do have degenerated levels, then the random wave approximation for sure will not work anymore, but still your bath could somehow, I don't know, show some ETH properties if you want, and thermalize in some sense and become truly a true bath, so to say, or not. And so maybe, I don't even know how to phrase my question here, but I find this a very interesting field to think about. So maybe you can add a few more words on, if you can, on these issues, because the words by themselves can mean different things. Either we approximate, or the bath is really incoherent, and so on.
So yeah, I want to say I agree with you. Yeah, okay. So even if we have the degenerated level, so where the random wave approximation cannot be applied, but we can imagine that some other decoherence the effect, right? So so in this work, actually I will introduce the decoherence factors in the coherent process, the considering that kind of the unknown background noise. So then I investigated the coherence can survive in that circumstance when we introduce another decoherence factor. So let's see. Yeah.
Yeah. Thank you.
Yeah. So after this talk, we can discuss the more, I think. Okay. Anyway, so yeah. So the one may ask that this coherence effect anyway. So if we assume the perfect heat bath coherence, then one may ask that this coherence effect can change the efficiency or some entropy production in the thermodynamics. So okay, so I also ask the same questions. So so in this talk, we discuss this kind of the systems possessing this coherence by the heat bath. But this is much complicated. I mean, we have to consider this kind of work agent. So to avoid this the complexity, I will use the quantum dot heat engine. So in this setup, we can consider about the another work repository, like the laser system. Okay, so it is very natural to get the insight of the heat and work in the very simple setup. So okay, I will explain. The quantum dot has the well-defined energy like this. In this work, the state, only one single state allowed in the quantum dot. And if tunneling between the dot and the reservoirs is allowed, and temperature gradient and chemical potential gradient are applied, it can be used the thermoelectric device to where the heat flux can be converted to power without, as I mentioned, extra work agent. Yeah, this heat engine is recently realized. Yeah, so the experimental setup was reported in this paper. In the weak coupling regime, even though this is a quantum system, but the all thermodynamics becomes the classical thermodynamics. This whole dynamics can be described by the classical master equation like this one. This P and P0 and P1 means that the probability for the empty state and the occupied state respectively, and this W means that the transition rate. So this superscript H and C means that the type of the bath, hot bath and cold bath, and plus means that the inflow from the bath to dot, minus is outgoing from the dot to the bath. Okay, so each rate, obeying the following the Arrhenius rule like this one. So okay, so I don't want show the detail about the solution of how to solve this equation and whatever things. I just want to show the solution of the steady state. They're very simple. So you can check this solution by putting them into this equation. Then you can find that immediately satisfy this steady state conditions. In the steady state, okay, right. In the steady state, incoming and outgoing particle current have the same magnitude, but the opposite directions. The magnitude is given by this simple form. So this is the So you can read the meaning of this equation. Anyway, so I want emphasize that the energy can be expressed in the particle current in this case, because the hopping particles carrying the heat energy of the heat bath. So heat rate is given by the product of the energy times current, and the power is also the chemical potential difference times the particle current. Oh, this is typo. Sorry. Okay, anyway, this is typo. So when we calculate the efficiency, then the efficiency is simply given by this ratio of the energy. This is independent of the current. So many studies are already done about this efficiency of the properties. So anyway, I want to say that this is very simple. Okay, so there is nothing this is nothing to do with any quantum, although the system, the title of the system is the quantum dot heat energy. So,
sorry, could you comment in few words about signs plus and minus? Because you have defined what is W plus, W minus, you have just defined the ratio. Could you just say a few words? Yeah, please. Yeah, thank you.
yeah, the plus means that the inflow from the base to the top. Plus means that the particle is hopping with this rate from the Hall reservoir to top, or this one is from the cold base to the top with this rate. The minus is the other way.
The minus is in opposite direction, hopping?
Yeah, right.
Okay, thank you.
So, to investigate the quantum effect on the thermodynamics, quantum thermodynamics, maybe we need the multi-dot setup, in series or in parallel. So, in this case, in this work, we just consider the thermal heat bath. Okay, so we don't consider any strange quantum bath. Just only the conventional thermal heat bath. So even though there are some coherent hopping between the quantum dots, this coupling is truly classical one. So the thermodynamics is just classical thermodynamics in this case. So maybe to investigate the quantum effect of thermodynamics, we need this kind of setup. So already there are some papers about this quantum dot setup, parallel the quantum dot coupled with this heat basis in parallel. So in this paper, the authors studied the quantum mass equations for the non-interacting multidot, and these papers authors investigate the symmetry in base dot coupling. So in this work, I take this parallel situation, and with this difference between the particles in the dot. So it means that if the particle is doubly occupied, then they feel the difference with each other. And I generalized this base dot coupling. Okay, so then maybe the Sergey can get some ideas, the coherent, the best effect. Anyway, so okay, so I also in this case, in the non-degenerate case, so yeah, people said that if we have non-degenerate energy levels, then probably rotating wave approximation will work, and there's nothing about the coherence. But if we drop this approximation, then we can get some strange mass equations, the time-dependent mass equation. Then probably there's something strange appears in the equations. So I briefly discussed something strange when we drop the rotating wave.
I have a short question. So if I look at this picture for the parallel arrangement, and then you have these two levels, E1 and E2, and there are two red arrows, double-sided, which point to them from the left, say, heat bath. Mm-hmm. Does that mean that these, how should I say it, these couplings, or so does it mean that I have two independent leads? So I have a big heat bath, and then I have, let's say, one lead which connects that heat bath to level E1. And then on the other side, I have the same heat bath, and it is also connected by a lead to level E2. Is that lead the same in some sense, or are these leads statistically independent.
So
Or is
yeah.
that, you see, because I could just think about one lead, which then couples to two dots, and then there's again one lead on the other side, which collects the stuff, and or vice versa. If it's one lead, then I can expect that I can get some interference effects. If these are two leads, which you draw here, which are, so to say, two different holes from a huge heat bath, which is connecting to two different levels, then the situation will be very different. So what do you have in mind here?
Okay, so each level has the different heat bath, then I expect that there is no coherent effect. Okay, so of course
So in other words, it's one and the same lead which couples to two levels.
Mhm.
Yes. Okay. Thank you.
So yeah, so here, so I just only consider the same heat bath coupled to the two or multitask at the same time. Okay, so the mathematically this is different. I mean, if we have the different heat bases associated to different level, then maybe we need some different bath operators. But here I just used one operator for the heat bath, so that point makes some coherence here. So I continue the top. So now I specify our model. The first I just consider single heat bath. So in this the Bakov, I mean the quantum mass equation level. So in the quantum mass equation level, where only we keep the second order the coupling, the generalized to the multi heat bath is just straightforward. I just add some another heat bath operators here. So I'll show you later. So this is why I just present the one bath situations. So this is the energy part, and this is the the Coulomb differential part. Okay. So this Hamiltonian is for the heat bath, and this is coupling. You can see this coupling is just hopping between the bath and quantum dots. So this bath can hop either the ice level and J's level at the same time. So okay, so the D dagger and D is the fermion. All the operators for the fermionic operator. Okay, in this case. So I just consider the particle bath.
And the fermions are spinless, I guess, right?
Yeah, for simple, I omit the spins, but yeah, the other works to consider the spins.
Sure.
But,
yeah. Thank you.
And the temperature is the definition of the evolution of the density operator, whereas temperature.
Temperature is defined. Okay, so in this case, I just assume the heat bath is in equilibrium, so temperature is well defined. I assume the heat bath density operators is constant in time. So the dynamics interaction between the heat bath and the quantum dot doesn't affect on the heat bath property. I just assume the very conventional so temperature is very naturally defined in that way. So this is the evolution of the total density operators, but I want the evolution equations for only the system density operators. So we just take the partial trace on the total systems. And here, I just keep the second order of the interaction terms. And yeah, of course, we have to apply some approximation to get this type of the master equation. So I just keep the any details. Anyway, we can have the this dissipator operators, right? This only the second order of the operators, right? The di dagger and d dagger and d is just the same, the fermionic operator of the dot, and I and j is the indices of the dot. Okay, so immediately you can see that there are some the mixed term, right? In the classical systems, this mixed term becomes zero. There's no in the classical systems only stochastic transitions exist, but in this case we have we can see this coupling terms. So okay, the briefly I want to say that if we have another heap basis, then we just add the heap basis Hamiltonian and another the hopping interactions, and after this same approximation, then we can get the dissipator term is almost the same the form of this one. So we just add one more the dissipators here. So if we have another and another, then we just put the similar dissipator operators here. So again, I continue to the single best case. Then the heap best property is included in this n functions. This function is nothing but just the Fermi-Dirac distribution, and E is the energy changed when the system is changed to transfer to another state. So for example, the system has the n particles, and another particle is coming in from the heap best to the system. Then the system is transit to the n particle state to the n plus 1 particles. And the energy changed is the dot energy. Here, I just assume that the degenerated dot. And another energy contribution is the charging energy from the Coulomb diffusion. Okay, so, right. So, using from this Fermi-Dirac distribution and this energy changed, so you can find the solution of in the steady state is just the equilibrium thermal operator. So you can check just simply putting this solution to the dissipator, then yeah, satisfying the equal to 0. This K is I just redefine the system Hamiltonian with these chemical potentials. Remainder is the same. Okay, so this is incoherent, right? Even though we have this coherent process, coherent interference, the steady state has no coherence at all, right? But problem is here. So I can rearrange this dissipator like this one. This is perfectly equivalent to this dissipator expression. Okay, I just put a summation inside of this bracket. Then, if you have the initial condition as the pure state, whole empty state, then and you can find that as time goes by, the system becomes the mixture of only these two states. Okay, this is because this mixture, this superposed state, the states by this relation. So if you put the sum of the accretion operator on this the superposed state, single occupied state, then you can find that always becomes 0. So there's no other transition from this single occupied superposed state. So steady state, really steady state is composed of these two states, full empty state and singly occupied superposed state. This is really that equal to the equilibrium density operator, right? If equilibrium density operator should have the double occupied state, the all mixture of the possible state, right? But if we start with this initial condition, then we end up this of the mixture of these two states. If you have another initial condition, then your steady state solution becomes different. This is initial condition dependency in the steady state, right? So this equilibrium solution is not unique in this situation. Right? Coherence, yeah, better in this case. So I consider to avoid this is very the unrealistic, right? We have just a single path. There's no we expect if we put your system in the just the summer the heat bath, then everyone expect the equilibrium system state, the system state in equilibrium, right? But you think of this parallel setup, then your solution becomes has the dependency of the initial condition.
May I ask you, what happens if you choose a different initial state?
So, for example, you just the fully occupied state, right?
Yeah.
Then the steady state is composed of the fully occupied state and this half-filled the superposed state. There is nothing.
So all states will happen in the will come up will realize in the steady state.
Depending on the initial condition, yeah.
Right. Yeah. So your initial so for different initial conditions, basically you get different steady states.
Yeah, in this case, so this that very unusual. I mean, very count the.
And could you again maybe explain in simple words what the reason for that is?
So if you have the full occupied state initially, then in the case this operator.
No, I don't mean in the details of the algebra here, but in so to say more simple words, what is the reason? I mean, you assume that you take a single bath on or two baths on both sides, and you look for a steady state solution, and of course we expect that there's just one, and now you figure out that things depend on the initial state. So what is the reason? Something went wrong. So what went wrong?
Oh, it's not wrong.
Yeah, it is wrong in my or your or anyone's arguing, because we were expecting something different. We get something else. So something went wrong in our argumentation. What?
But I don't get the point. I mean, this consequence is just the mathematical consequence, right?
Yes. Yeah.
Yeah, but
discussions before, sure. But what is it? I mean, is it that there is some strange interference which enters the game, which makes your steady state not unique and initial state dependent?
Yeah, but my point is it's not the coherence is big one. I mean, it's not my point. My point is that if we consider the very small disorder in this system, then this initial condition dependency is disappear. Only the equilibrium state is the
disorder in what, please?
If we consider any small disorders
disorder in what? Well, where do you place the disorder in?
So in this stage, I just consider the phenomenological parameters, but
But
Yeah,
what
so-
would that mean then in a real system? What kind of disorder do I have to add to this?
Yeah, the
setup?
phonon can be one. It can be phonon. It can be gate noise. So whatever the background noise.
So basically, what you say is you want so this extra noise, these extra additional phonons, gate noise, and so on. They will affect what? They will affect the bath itself, or what?
The coupling between the path and
The coupling.
the dot. Yeah.
Mhm.
The okay, so
Okay. Yeah, I think I understand a little bit. But let me ask again, because I'm not sure whether I heard the answer correctly or not. So is the current paradox, let me call it the paradox here, is that due to destructive interference effects, or constructive, but mainly also destructive interference effects, which can happen when you look at the propagation of excitations from the hot to the cold bath, or is this interference? I mean, you see what I mean is that you have a bath, sure, but then the bath is essentially a set of degrees of freedom, and now you take basically a particle which can now tunnel into one of the two levels, and then so it has, and then it can continue its path to the other lead, into the other lead, and that just means that you have two scattering paths, which leads to Farner resonances and the such. Is that something which is related to this kind of paradox which you observe here, or not?
So
Okay, if you cannot tell right now, let's just continue. I don't want to interrupt your lecture, but we can maybe try to figure that out later.
Sorry, Jaegon, isn't this a much simpler thing? You simply have a symmetry in your system. Your two dots, you can interchange them. It's a very simple symmetry, which is what is causing a degeneracy at the end. And that is it. You have multiple steady states. And in this case, you would have two steady states given the structure. That's it. So, I mean, why are you attributing all this to coherence and all these factors? It's a very simple symmetry issue.
So Josar, you say that actually, okay, I probably missed that point. So we look at the degenerate case, and you say there is a symmetry.
Yep, you can interchange the two dots and everything remains the same. You have a symmetry in your overall system, meaning your combined system, which means that if you look at the generator of your dynamics, you will be able to get a block diagonal structure. In this case, you will get just two blocks, both will have a steady state, and that's it.
So you have two steady states, basically.
You have two steady states, and hence, depending on the initial condition you start from, you can end up with any one.
Right.
And if you start with something which is completely a superposition of these two steady states, you will end up in a superposition. So, you know, you can end up in any state that you like.
And Farner resonances are not needed here at this level.
No, and I don't think it is also, I mean, you will get a coherence as a consequence of such symmetries, but it's a consequence of symmetries, I feel. Sorry, Jaegon, any what's wrong with this argument that I just provided?
okay, so yet I didn't get into the symmetry argument because it's just a single path situation, so there's no other. Anyway, so let's go to these situations, the two level engines. I mean, previously I didn't mention about the engine. Okay, just that system coupled to the heat bath, single heat bath. So it cannot be the engine. Okay, now I consider the engines with the two different heat baths, right? This dissipator is associated with the hot heat bath, and this dissipation operator is also associated with the cold heat path. So everything the same, but the difference is just the this combination of these two path operators. So everything can be different, will be different. I mean, okay, so okay, but just start with this diagram. So we have two heat paths like this one. Okay, so we have the two quantum dots. Here, the W is just equivalent to the classical transition rate. Okay. Of course, this is derived from these quantum operators, and other transition rate are derived from this quantum mass equation. This one, this and this one. So this here, the 1 and 2 is obviously denotes the dot index, but this coherent process has a mixed index in the indices of the dot. So usually this process cannot be described in the classical mass equations. So for example, each rate is following this classical Arrhenius rule, but we have this strange transition rate. We cannot describe this whole dynamics as the classical populations. This is rho 1,1 and rho 2,2 is just population of the state, and this 0 is the empty state, and 1 is the occupied first dot, and this is occupied second dot, and this is double occupancy. Okay, so I just skip all details. I just want to say that if we have to solve this 6 variables in the classical system without this one, we only have to solve these 4 density operators, right? So the steady state, whatever thing, evolution and steady state, whatever thing is, we just solve this 4 the variables. But with the coherence terms, we have to solve the 6 different 6 variables. So equation of motion is basically described these 6 variables. Okay, so here symmetric argument coming in. If we have the symmetric couplings between the dot and hot bath and cold bath, right? The symmetry means that if here we have this coupling constant between the dot and bath, and can be different, but they are the same, and also the decoherence factors are same. Then all situation is equivalent to the single bath in the degenerated case. So every solution have the same structure of the single heat bath. This means that there is no coherence, except for this perfectly coherent state. Whatever this, no matter how much the disorder is introduced in the system, then the coupling between the dot and bath is contaminated by the disorder. Then we can have the incoherent classical steady state solution, unique steady state solution, except for if the system is is perfectly clean, then if we assume our system is perfectly clean, then we can find the initial context dependency dependent the steady state solution, but very rare, right? How can we make the clean system? Anyway, but in general, okay, in general, without this symmetry condition, this rho 1, 2 and rho 2, 1 becomes non-zero. Okay, even though we consider these decoherence factors. This is the point of this work. So we can expect the coherence effect of the thermodynamics due to this coherence, because this coherent the coherence term will not vanish in the steady state, in general situation, we can expect some the coherent effect on the thermodynamics. So first, I calculate the particle current. So to calculate the particle current, I first started with the average number. This is 0, 1, 2 is just the particle numbers, and rho 0, 0, rho 1, 1 is just the populations of the state. Of course, taking the time derivative, we can see that this is always 0 in the steady state due to this each component becomes 0. Right? But we can divide the contribution from the hot bath and cold bath, like this one. This is balanced but a different direction. So we can gather the this red one and blue one. We can define the current from the hot bath and dissipate it to the cold bath. Exactly same, because I only consider the steady state. So this is a simple example. If we consider infinite U region, then the double occupancy is not allowed. So the all particle current is just becomes this single particle current. So I calculated this all the quantities. In this case, I just for simplicity, I just choose the real parameters. So this the coherent spectrum becomes real here. So I can divide the current into the classical part obtained when the pi becomes 0, and the another part, it should be the contribution from the coherence. Fortunately, this part is directly proportional to this coherent part. So I can divide the current into the classical one and this quantum current. So I calculated numerically these equations. So I found that the quantum current can be positive or negative. So this situation is the symmetric coupling, and this situation is asymmetric coupling case. So here the diagonal, this figure is the in terms of the decoherence factors. So decoherence parameters. So this diagonal means that this the symmetric coupling cases. So there is no coherence. Anyway, so this is practically important because the power of the heat and this quantum dot engine is directly proportional to the particle current. So if you finding the optimal current it can be important in the practical sense, because the most fattest the engine become maybe the most powerful engines in this case. Okay, so now as I mentioned, the power is proportional to the particle current, right? So in this model, the energy flow can be expressed in terms of the current. So again, I started with this average the energy the definition. So this is that energy, and this is Coulomb diffusion. So yeah, of course, taking the time derivative, that this average energy time derivative of the time, the average energy is also 0, with the same region with the particle current. But I can separate. But we separate the current, the population currents from the hot bath and cold bath, like this one. So this is minus, means that the energy flow from the cold bath, right? So inserting the chemical potentials here, so I can define the heat rate from the hot reservoir, and another thing is the dissipated heat rate to the cold bath, and here I can define the work. So using this expression, I can calculate efficiency. So W dot divided by QH dot here. So I rearrange this input heat rate like this one. This J is the particle current, and this is the population current for the double occupied state. So if we take the zero interaction, then this is nothing to just become the classical efficiency, right? So just,
Sorry, Jaegon, a quick question.
Yeah.
How are you equating the energy current to be the heat current? So like, how are you getting the heat current here? Don't you need the entropy or the entropy production? You're simply minusing the particle current. Is that all? You're just using the first law.
It's just first law. Yeah.
And so the way you get this heat, does it already satisfy the second law now? In this particular way you have defined heat?
Yes. This quantum mass equation always the positivity of the Clausius entropy, because this mass equation.
No, that is true. That is only true if you define the energy current as that leaving from the bath. What you have defined your energy current as is energy of your system. Okay. So in this case, does it still follow the second law? That's the question. Normally, sorry, it follows.
It follows second law. Yeah.
Okay.
Yeah. So
thank you.
This quantity is also can be derived from the non-negativity of the. Okay. Anyway, so okay. So I will again mention about the second law. So, okay. So efficiency is given by this term. So I just using the thermodynamics first law. I divide the heat and work from the energy flow, and make the efficiency like this one. And here, if we take the symmetric couplings and take the full coherence, then this double occupancy can be eliminated when we started with the empty state, right? As I show you, if we have the empty state, then the steady state only contains the empty state and the mixture of the single occupied state. There's no double occupancy. So this J3 becomes 0 in the case. So the efficiency becomes this delta mu divided by E minus UH. UH is this chemical potential of the hot reservoir. Of course, this efficiency is is larger than the classical one, and because in the classical system, without the coherent vector, the J3 can be positive in the classical system, but in the quantum system, and when we arrange the coupling in symmetric way, and of course with the perfect the coherent process, then we can find some steady state without this the current with the double particle current. Okay, then we can get the higher efficiency than the classical, right? But this efficiency is it turns out that bounded by this current efficiency by the calculation. So whatever you have this symmetric coupling, the efficiency is bounded by this current efficiency. Okay, so you may ask that if this parameter becomes close to this current efficiency, and coherence can make this current negative, then you can you have the more efficiency than the current efficiency. Okay, it becomes negative. Then I said we can set the parameters to this energy ratio is very close to the current efficiency, and we change the parameters. Some other parameters make this current negative. Then the resulting efficiency can be larger than current efficiency, right? Just imagine that. But it's not possible. Okay, so I didn't say that this vast equations obeys the positivity. But the positivity, the obeying guaranteed positivity means that the Clausius entropy, this Q dot and QH dot and QC dot is exactly the same with these quantities, satisfies this positivity. Clausius entropy is always the non-negative. So from this thermodynamics second law, we can get the higher efficiency than the Carnot efficiency. This is the result of the degenerated engine. Okay, so no matter how much you put the coherence in the system, you cannot get the more efficient engine than the Carnot engine. You cannot. So to get the more efficient engine, so we have to drop the rotating wave approximations. So yeah, you can ask the reality of the dropping the rotating wave approximations, because the heat vest has the many degrees of freedom, and they are very abundant of the so many the noise we can account. So rotating wave approximation is very reasonable, right? If we have the thermal pass. But anyway, so we start with just dropping the rotating wave approximation with this non-degenerated energy levels. So just let's see what happens. So this is again, this is the vast equations with these simple situations. Then Lindblad jump operator is just four operators. So given by just four operators. So the quantum mass equation is simplified like this one. So with this coherent process, we have the effective hopping here, and this gamma matrix is just dissipator's coefficient here. So usual quantum mass equations, the gamma matrix is a positive matrix. Okay, so only we expect the Clausius entropies, the non-negative Clausius entropy from this positive gamma matrix. But in this case, if we drop the rotating wave approximation or scalar approximation, this element becomes like this one. Here the off diagonal has this additive form. So we can just test if just put some constant here, so, and calculate the determinant of this submatrix or Blanc matrix, then we can get the negative determinant in this case. It means that this Blanc matrix has the one negative eigenvalues. Okay, so this means that this matrix is cannot be positive matrix, can be the negative matrix, and complete positivity of this dynamics cannot be guaranteed in this case. So here the implication of this result is that the negative Clausius entropy is possible, and also negative probability is also possible. This is very weird thing, right? The negative probability. So negative probability should be limited by something, the Markovianization or whatever things. But negative Clausius entropies should be fine. Would be fine, I think, because maybe there are some extra entropies to make the thermodynamic second law. So we don't worry about this negative Clausius entropy. We can exploit this negative entropies using this. So I checked really in this system, so we can get some negative entropy or the more than Carnot efficiency. So I calculate the simple calculations. So really I get the negative current. This one. So the total current is from the hot reservoir to the cold reservoir, but the some part becomes the backward current. So this becomes negative. So really, I can get the more efficient engine than the current efficiency. But we have to careful this limit. If we have the negative density operator, then this is just garbage, right? So we have to careful to avoid the negative density operator region. Anyway, so I checked the positive density operator region. I can get the negative entropy production and the more than the current efficiency. So probably my next job is the seeking of this additional entropy terms to satisfy the thermodynamic second, to modify the thermodynamic second law, because entropy cannot be negative, right? Rate of the entropy rate is cannot be negative, right? At least it becomes 0. So in this Clausius entropy, if this Clausius entropy become negative, then should be there are some compensation of this entropy, negative entropy. So probably we can find these additional entropies. Okay, this is a summary of this talk. So I have investigated the coherence effect with the multi-level quantum dot heat engine. And under the rotating wave approximation or scalar approximation, coherence can be survived if we have the degenerated engine. So, but the efficiency is bounded by classical current efficiency. And without rotating wave approximation, maybe we can get some more efficient engine, but we have to careful the positivity of the density operator. So this is my ongoing project. So I try to limit of the negativity of the density operators. Probably the Markovianization can be worked. Just stepping up the dimensionality. Maybe you know the Maxwell-Demon problems. The demons exploiting the information of the system can induce the negative entropies. But if we introduce the entropy of the demons, then the total entropy production should always the positive. So this kind of the Markovianization adding up to some dimensionality of the system. I expect the same procedure can work in this system. Thank you.
Okay, thank you, Jaegon, for this talk. Let's thank our speaker. There we go. Time for questions. Okay, maybe till the time somebody raises their hand. I have a quick question. So in this last part, you were talking about this entropy production rate. And what is the problem with the entropy production rate being negative? This can always happen. Entropy production rate, there is no problem in negativity of entropy production rate. The entropy production itself cannot be negative. The rate is okay to be negative. So I think you always had the rates because you always had the Q dots in there.
The original thermodynamic second law.
Yes, it's with entropy production, not with the rate of entropy production.
No,
so the
rate of the entropy production.
No, the rate works only. So the rate is true that it is positive only for a CPTP map. For a non-CPTP map, the entropy production rate can always be negative, but entropy production itself has to be positive. The integrated one, the integrated quantity.
Yeah, CPTP map. Yeah, right. The positivity of the entropy production, not rate, but Lindblad equations can be defined. Yes. in terms of the rate of the entropy.
Sure, because that is a CPTP, and there you can explicitly prove that the rate is positive.
But the Lindblad,
Mhm.
Lindblad equation is the just dynamic map. I mean, we can
Yes.
divide the operators in infinitesimal time. So every time steps, we can get the positive entropy production. It means that the positive entropy production rate, right?
No.
Lindblad equation, the property of the Lindblad equation.
So there are two different things. Lindblad equation is completely positive as an equation, and it has a property of convexity. This convexity property is what leads to a positive entropy production rate because of the Lindblad equations. In general, if you have positive dynamics, you don't have a CPTP map, and hence you can always have positive entropy production, but the rate can be negative. Think of an oscillatory function. Okay, so if it goes up and it comes down, when it is coming down, the rate is negative, but it can still be above a zero. You know, the whole function can always be above some zero. So this is exactly what happens with non-CPTP maps, that you get negative entropy production rates, but your entropy production is always positive. Okay, maybe we can discuss this later if you would like to do this, but let's see if there are any more questions from the audience at this point.
Could I ask a few transparencies before this one? You define the number of particles, I think, in hotbeds and related to the average number. Something I was asking about double plus and double minus, the same ratio. Could you just show? I will ask before. Yeah, yeah, exactly. This was what I call Arrhenius law, a rule. What does it mean? The number of particles related to the equilibrium number of particles can be such a huge difference? Due to what? I'm talking about this, what you call Arrhenius rule.
Mm-hmm. This
well,
is
what is this?
Arrhenius rule is coming from the equilibrium property of the thermal bath. So I assume that heat bath is always in the thermal equilibrium, and to get this mass equation, we have to calculate the correlator of the heat bath operators. The result of the calculation is always given by the Fermi-Dirac distributions. Fermi-Dirac distribution is satisfy this Arrhenius rule, right?
No, it's okay. What I'm asking is n. This n capital is this what? The number of states of particles. What is it?
So n is defined in this way. The number operator of the heat bath.
Okay, and this number in equilibrium, there is some number, and then you're saying that due to the temperature, the number can vary in such a way as Arrhenius rule. So many particles can escape, but you have only place for a couple of particles in your quantum dots. This okay?
Yeah. It's nothing to do with the 1 and 2, the plus and minus. It's just defined by obtained from the heat bath.
Okay, so.
Okay. So I don't see any further raised hands from the audience. So with that, maybe we thank our speaker once again. Let's see. Okay. So thank you, Jaegon, once again for this wonderful talk. We take a short break for 5 minutes and then come back for the discussion session. but officially we end the PCS 7 hour. So thank you all for joining.
In 5 minutes.